Now, edge illumination. What I'm about to say applies for any feed pattern, so we're not limited to cosine Q here. This works for any feed pattern. For an axisymmetric paraboloidal reflector, edge illumination is defined, this is the defining relationship, as the electric field magnitude incident on the rim to the electric field magnitude incident on the vertex. So here's a reflector, here's the feed. We get a value here, which is in the denominator. We get a value here at the rim, and the ratio of those two things is called the edge illumination. So the edge illumination is saying how far or how much less the magnitude of the electric field is at the rim than it is at the vertex. Now we know that the electric field incident on any point in the reflector is proportional to the normalized feed pattern and inversely proportional to the distance from the feed to the point on the reflector. So just to remind you here, this is theta sub f, this angle here, and then this distance is r sub f. So we can use this to get an expression for edge illumination. Because we're simply saying this is proportional, we can forget all the other constants because they'll divide out when we take the ratio. In the numerator, we evaluate this for theta sub f equals theta sub naught, in other words, at the rim. In the denominator, we evaluate this for theta sub f equals 0, in other words, the vertex. Now in the vertex, r sub f is just f, just the focal distance. And the normalized feed pattern at the vertex is simply 1, so the denominator is pretty simple. In the numerator, r sub f at the rim, we have an expression for, and it's simply this. We don't have a simple expression in general for this, so we simply carry this over. And now we do a little bit of math, and we find that the edge illumination is 1 plus cosine theta naught, again theta naught, the angle to the rim, divided by 2, times the normalized feed pattern evaluated at the rim. So this is a relatively general expression for edge illumination. If we apply it to the cosine Q feed model, then this is the edge illumination. Now there's a 1-to-1 correspondence between angle to the rim and f over d for axisymmetric paraboloidal reflectors. So if we state the f over d, that immediately constrains theta naught, the angle to the rim. And then we can calculate the edge illumination if we know Q. So, for example, for f over d equals 1/4, we know the angle to the rim is 90 degrees. Now, keep in mind here, the feed model for cosine Q always has a null for theta sub f equals pi over 2. So, in that case, we get edge illumination is 0, that is minus infinity dB, regardless of Q, if f over d is 1/4. Now, if f over d is larger than 1/4, then theta naught is less than pi over 2. And then we get edge illuminations like this because we get a non-zero value for the electric field incident on the rim. And then as f over d increases, theta naught decreases, and the edge illumination goes up. Now, Q equals 2 is representative of many feeds encountered in common practice and therefore is often used as a reference case. I'm not saying that this is true in general. I'm simply saying that in the absence of other information, it's common to use Q equals 2 as a starting point. Now, if Q equals 2, then we know the directivity is 10, which is the same as 10 dBi. And since we've now chosen a feed model, and we've constrained the reflector to be axisymmetric, the design is now parameterized in terms of a single independent variable. That is, we've got these three things, f over d, theta naught, the angle to the rim, and edge illumination. If we state any one of these three things, in other words, if we say f over d, then right away we know what the other two things are. If we specify theta naught, then we know right away what f over d and edge illumination are. So again, if we choose the feed and we require the reflector to be axisymmetric, then constraining any one of these three quantities immediately determines the other two. Useful idea for design. If we choose a cosine squared feed, Q equals 2, and we plot illumination efficiency as a function of edge illumination, we now have a single curve. As edge illumination goes from 0 to minus 25 dBi, that's taper efficiency going from 1, right? Because edge illumination of 0 means the edge gets the same magnitude as the vertex. That's perfect taper efficiency. As taper efficiency goes down, then so too is edge illumination going down. However, spillover efficiency is going from 0 when the edge illumination is 0 up to 1 as edge illumination gets less. Illumination efficiency, which is the thing we're ultimately interested in, is the product of those two things. So illumination efficiency starts off low, climbs, reaches some maximum, and then starts decreasing again. So it's evident that there's a broad maximum where the illumination efficiency is optimized for this particular choice of feed. Now it's a broad maximum, but we see in general this is pretty close to about 11 or minus 11 dB. That corresponds to an F over D of about 1/2, for which we find the illumination efficiency is about 82%. Now, what is it for other feeds? In other words, what if we don't have Q equals 2, or what if we don't have a feed that's well modeled as Q cosine Q? Well, in that case, we find the optimum illumination efficiency is still about 82%. This turns out to be true for values of Q from about 1 to about 4. And this you can determine using the same method that I've just used here. Now, this value is obviously not exactly 82%. It goes up or down a little bit. But this is a pretty good starting point if you have to guess a value. In practice, one usually finds the best outcomes illumination efficiency of about 75%. So slightly less than 82%. And this is for a whole bunch of reasons that pertain to practical implementations. There are errors in alignment or in mounting the feed and so on, so that the actual illumination is less. So 75% is a pretty good starting point if you have to guess what that value is going to be. Now, simple feeds like open-ended waveguides, which can be used as dish feeds, are far from optimum, and so that when these are used, we typically get a best case illumination efficiency of about 60%. So why am I saying all this? Well, this is kind of a known value for about as good as we can get. This is a typical value for a well-designed reflector. And then this is a typical value for a reflector antenna system where we have to make some hard compromises, like using a very poor feed, such as an open-ended waveguide. Now let's try to summarize this and generalize the results just a little bit. Directivity for a large aperture can be expressed as the directivity of a uniformly illuminated aperture times the aperture efficiency. Now, the directivity of a uniformly illuminated aperture, which is ideal, by the way, in terms of maximizing the directivity, can be written as 4 pi over lambda squared times the physical aperture. The aperture efficiency can be written as the product of 3 things. One is the illumination efficiency, and that's what we've been spending our time in this lecture calculating. And we found values ranging from 82% to about 60%. Radiation efficiency, which is what this is normally very good for reflector antenna systems. In other words, it's fairly common to be able to design feeds which have very, very low internal ohmic losses, so that typically we can assume that this is about 1. Now maybe it's 99%, but that's still very close to 1 compared to other numbers that we're using here. This quantity here is something known as achievement efficiency. We'll be talking more about this in a later lecture, but the idea is that this captures all the other things that we've neglected here. For example, polarization losses, cross-pole efficiency. Surface roughness is another thing we have not considered. So all those other effects we're lumping in this thing, achievement efficiency, and as a starting point, we'll assume that's about 0.9, which is a typical value, about 90%. So when you multiply all three things together, that gives you a good estimate of the aperture efficiency, and so we can compute some typical values. Typical is 74%, common is 68%, and also common, but representing a reflector antenna which is not particularly well designed, is 54%. So this is a common range of values of aperture efficiency for paraboloidal reflectors. This concludes this lecture on optimal illumination of axisymmetric paraboloidal reflectors.